Welcome back. I'm Dr. Tullis. We are kicking off Chapter 13, Section 3. We will describe the effects of pressure and temperature on the solubility of a solute, use Henry's law to calculate the solubility of a gas in a solvent, and apply Le Chatelier's principle to predict the change in solubility of gases with temperature changes. Pressure and temperature are two external factors that influence solubility. Both affect the solubility of gases and liquids, whereas only temperature is a factor in the solubility of solids in liquids. Henry's law looks at dissolving gases in liquids. The solubility of a gas in a liquid is directly proportional to the gas pressure. Henry's law states that the solubility of a gas is equal to Henry's law constant times the partial pressure of the gas over the solution.
In this video, we're going to take a look at an important law of respiratory physiology called Henry's law. Now, we've spoken about Boyle's law in a previous video, we've spoken about Dalton's law in a previous video, now it's time to talk about Henry's law. Now, Henry's law states that the amount of dissolved gas in a liquid is proportional to its partial pressure above the liquid. So first thing is partial pressure. We spoke about partial pressures when we looked at Dalton's law. But just to reiterate, remember that if we take all of the atmosphere around us, it is exerting a particular pressure on us. Now that pressure that all the gas together is exerting on us at what we call sea level ends up being 760 millimeters of mercury worth of pressure. And Dalton's law states that this pressure is simply a sum of all the individual gases. And we know that there's nitrogen, oxygen, carbon dioxide, and other trace gases. If we just focus on oxygen and carbon dioxide, for example, in this video, we know that oxygen, O2, right? Oxygen makes up 20.9% of all the gases in the atmosphere around us. And carbon dioxide makes up 0.04% of all the gases in the atmosphere around us. Now, if we take 20.9% of 760, we end up getting 159 millimeters of mercury. So that means the partial pressure of oxygen in our atmosphere is 159. That's what partial pressure is. And sometimes you'll see it written with a P in front. So you might see PO2, that's saying the partial pressure of oxygen, at least in our atmosphere, is 159 millimeters of mercury. What's the partial pressure of carbon dioxide? Well, 0.04% of 760 ends up being 0.3 millimeters of mercury. And that's the partial pressure of carbon dioxide in our atmosphere. All right, now let's take a look at Henry's law, which is stating the amount of dissolved gas in a liquid is proportional to its partial pressure above the liquid. So we need to draw a container that's got liquid in it. Now let's give an example here where we've got the atmosphere. So we know now what the concentration or the partial pressure of carbon dioxide is outside. So let's use another pen. Let's say the PCO2 in the atmosphere is 0.3 millimeters of mercury. Let's say in here, in the liquid, the PCO2 is 45 millimeters of mercury. Now this is where partial pressure, Henry's law, all comes into play. Gases will only move down their own pressure gradient. Gases will always move from a high pressure to a low. I always say to my students, think of a slide. You've got a slide where it's up the top and down the bottom, and you've got this nice ladder that they need to climb up. If you've got carbon dioxide sitting at the top of the ladder, it costs it no energy just to let go and slide down from where it's of a high pressure to down where it's of a low pressure. Or if you watch the news and you watch the weather and they say, oh, a high pressure system is moving in, high pressures always go to low pressures because it costs no energy and it wants to equilibrate. It wants to balance things out. So keep that in mind. So if we take a look at this now and apply Henry's law of partial pressures, knowing gases go from high to low, in what direction is this gas going to move? It's going to move from its highest pressure inside the liquid to its lowest pressure outside the liquid. So the gas will diffuse out, right? That is Henry's law in action, looking at the partial pressures. What if we take oxygen, for example? So let's say we've got the partial pressure of oxygen in the atmosphere is 159 millimeters of mercury. And let's say the partial pressure of oxygen in this liquid here, the PO2, is equal to 100 millimeters of mercury. Which one has the highest partial pressure? Outside here. So oxygen moves down. Again, its concentration gradient or its pressure gradient, its partial pressure gradient to apply Henry's law. Have a look. What's happening here? The partial pressure of carbon dioxide does not affect the diffusion of oxygen. And the partial pressure of oxygen does not affect the diffusion of carbon dioxide. And in this scenario, they're diffusing in opposing directions. Does this remind you of anything? It should hopefully remind you of an alveoli and the blood moving past. We've taken a breath in. We're going to have oxygen in here, and we want that oxygen to diffuse into the blood. So it must have a higher partial pressure in the alveoli than it does in the blood, so that it can go down its pressure gradient. What about carbon dioxide? We've just produced that in the body, so it's coming past. We want that carbon dioxide to go from the blood into the alveoli so we can breathe it out. So the partial pressure of carbon dioxide in the blood must be higher than the partial pressure of carbon dioxide in the alveoli. And again, it can diffuse out. This is Henry's law in action. It's important. So the water here is synonymous with the respiratory membrane, that of the alveoli and the bloodstream. Now, think of the application of this in different contexts. You go deep diving, the partial pressure changes because the atmospheric pressure becomes greater. So instead of it being 760 millimeters of mercury, it could be double that. That means the partial pressure will double. That means, for example, more gases will diffuse across a membrane, right? So think about nitrogen. Nitrogen is just this inert gas which does diffuse across, but we don't utilize it, so it's not a problem. But it's not a problem at 1 atmosphere. When that increases and that nitrogen moves in, it can then form these bubbles. And think about it. You go deep diving, the pressure is greater and greater and greater and greater. And all this nitrogen gets pushed into the bloodstream because instead of nitrogen, which is out here, so the partial pressure of nitrogen being around about 597 millimeters of mercury, going and then diffusing down its pressure gradient into the blood, it doubles. So more nitrogen goes into the blood. Now, this is when you're deep diving. What happens when you want to go back to the surface? The pressure slowly drops. This nitrogen then wants to go out again. And it's like opening the bottle of a soda can. Psh, psh, all those bubbles are formed because you're changing the partial pressures between the environments. And that's when we've got those nitrogen bubbles that can be forming. So again, it's all important when it comes to the context of the atmospheric pressure. But again, Henry's law needs to be applied. Think of what is the partial pressure. Hopefully that makes sense.
Here's a table of just some of the Henry's law constants of gases at 25 degrees Celsius. We'll refer back to them. Think of a can or a bottle of your favorite pop or carbonated beverage. This illustrates how Henry's law works. These beverages are packed under pressure in a chamber filled with carbon dioxide gas, some of which dissolves in the beverage. When the can or the bottle is opened, the partial pressure of CO2 above the solution drops, causing the solubility of the carbon dioxide to drop. Gas bubbles out of the solution. You think when you twist open that cap, or if you pop the top, you hear tss. That's that gas that's being released. After some time, an equilibrium between dissolved CO2 and atmospheric CO2 is reached. The beverage tastes flat when most of the dissolved CO2 is lost. And we can see the CO2, the carbon dioxide gas that is coming out of solution. Let's look at a Henry's law problem. Let's calculate the concentration of carbon dioxide in a Mountain Dew drink that's bottled with a partial pressure of CO2 of 4 atmospheres over the liquid at 25 degrees Celsius. Henry's law constant at this temperature is 3.1 times 10 to the negative 2 moles per liter atmosphere. Using Henry's law to find the solubility of that gas, we're going to take the constant that we're given, and we're going to times it by that partial pressure, the 4 atmospheres. And we would get 0.12 moles per liter, and moles per liter is also a unit of molarity. Let's look at this problem. What is the concentration of oxygen in a freshwater stream in equilibrium with air at 25 degrees Celsius and at a pressure of 1 bar? And express it in grams of oxygen per kilogram of water. We're told that we are at a pressure of 1 bar, so I need to find a few things. To find the solubility of that gas, I need to know Henry's law constant for oxygen at 25 degrees Celsius. I'm going to go back and look at that table, and I found that it was 1.3 times 10 to the negative 3 moles per kilogram bar. I also need to find the partial pressure for oxygen at 25 degrees Celsius. And in order to do that, I need to look up the mole fraction in air at 1 bar. And I found when I looked it up, so you had to look up the partial pressure of oxygen at 25 degrees Celsius with the pressure of 1 bar. It would be 0.21 bars, which is that partial pressure. Multiply those two together, and I got 2.73 times 10 to the negative 4th moles per kilogram, because bars and bars will cancel out. But it wants our answer in grams per kilogram. So all we need to do is to go from moles to grams, and we know that 2 oxygens have a mass of 32. So I got an answer of 0.0087 grams per kilogram. This one is a nicer question. What is the concentration of CO2 in water when the partial pressure is 0.33 bar? I like it when they give us the partial pressures. First we need to look up the Henry's law constant for CO2, and we would find that that would be 0.034 moles per kilogram bar. And we're told that the partial pressure is 0.33, so we just need to multiply those two together to get 1.1 times 10 to the negative 2 moles per kilogram. Let's look at solubility versus temperature. Gases dissolved in liquids. The solubility of all gases decreases with increased temperature. It's possible to predict the effect of temperature on the solubility of a gas from the enthalpy of solution. When gases dissolve in water, they usually do so in an exothermic process. This shows an equilibrium reaction between gas and liquid solvent. Here's our gas and liquid solvent. Think of your bottle of pop. On the left side of the equation, gas dissolves in our liquid, so that's our plus sign. Gas is dissolving in our liquid to form a saturated solution, which is our right side of the equation. And energy is released, showing energy as the product. The delta solution H is less than 0, which means exothermic. Delta H is less than 0, that means that it's negative, so it's releasing the energy. The arrow from right to left shows the reverse process, the loss of dissolved gas molecules from the saturated solution, and it requires energy. The reverse process, which is the loss of the dissolved gas molecules, requires energy as heat. At equilibrium, the two rates of the two processes are the same. Now let's account for the effect of temperature on solubility. We turn to Le Chatelier's principle, which states that a change in any of the factors determining an equilibrium causes the system to adjust by shifting in the direction that reduces or counteracts the effect of the change. If a solution of a gas in a liquid is heated, for example, the equilibrium will shift to absorb some of the added energy. So we could then say, if I increase temperature, that means we will shift left. And it will shift left because energy is absorbed in the process that produces free gas molecules and pure solvent. That shift corresponds to less gas dissolved and a lower solubility at higher temperatures. Let's look at solids in liquids. The solubility of solids in water is also affected by temperature, but unlike the situation with gases, there's no general pattern of behavior. The solubility of many salts increases with increasing temperature, but there are lots of exceptions. Chemists take advantage of the variation of solubility with temperature to purify compounds. An impure sample of a compound that is more soluble at higher temperatures is dissolved by heating the solution. The solution is then cooled to decrease the solubility. When the limit of solubility is reached at the lower temperature, crystals of the pure compound form. And if it's done slowly and carefully, it's sometimes possible to get very large crystals. Here we can see ammonium chloride dissolved in water, And we can see the ammonium chloride precipitating when the solution is cooled. So we can see those crystals. And notice our graph over here, we can see lots of these compounds' solubility increase with increasing temperature. But we've got a few down here that actually decrease, and this one looks like it hardly increases, about stays the same. Let's look at a few join-ins. The enthalpy of solution of sodium hydroxide is strongly exothermic. As the temperature increases, the solubility, we don't have a general trend for the solids. Again, most solubility increases as temperature increases, but we don't have that as a set rule. And in this case, sodium hydroxide, it actually decreases. The effect of temperature on solubility can be explained using Le Chatelier's principle. Le Chatelier states that if a stress, like heat, pressure, concentration of a reactant, is applied to an equilibrium, the system will adjust, if possible, to minimize the effect of the stress. Consider the case where the solubility process is endothermic, where heat is added. So it's part of the reactant, so it's absorbing. An increase in temperature puts a stress on the equilibrium and causes it to shift to the right. The stress is relieved because the dissolving process consumes some of that heat. So the solubility, or the concentration, increases with an increase in temperature. If the process is exothermic, a temperature rise will decrease the solubility by shifting the equilibrium left. So therefore, this is telling us that our reaction is going to shift to the left. So it would decrease that solubility. We would then need to absorb some of that. So that heat is a product. So if we increase temperature, we would need to shift to the left, which means that we need to absorb energy, making its solubility decrease. When the temperature is increased, the solubility of most gases, hopefully remember that it decreases, and the solubility of most solids increases. And the last one, after a can of carbonated soft drink is removed from the refrigerator, opened, and left to stand for a while, which of the following best describes the changes that cause the soda to go flat? Hopefully you said that it was lowering the carbon dioxide pressure over the solution and the raising of the temperature.